Okay, so we are going to be thinking about the vector cross product. We'll also need to think about the dot product. So, first of all, the dot product if you have two vectors, let's say our vectors are A, B, and C in 3 dimensions, and D, E, and F, then when we do a dot product, we simply do A times D, and we add B times E, and we add C times F, and we get out a number, we get out a scalar. And so this equals a number. Now the dot product can easily be applied to a vector of 2 dimensions. If you have A, B dot x, y, then the dot product is ax plus by, and again it's just a number. And what it means is if you have two vectors, let's call them vector A and vector B, then A dot B is equal to the length of A multiplied by the length of B multiplied by cosine of the angle between them, cosine of theta. And that works no matter how many dimensions you have for your vectors A and B. Now the cross product is actually quite different. So the cross product works for vectors in 3 dimensions. Apparently it also works for vectors in 7 dimensions, but really it's something for 3 dimensions in terms of the way we meet it most often. And in 3 dimensions, I'm going to be challenged to draw this, but let's have a go. Normally with 3 dimensions, what we have is x going along horizontally like that, z going vertically up, and y going into the page. Just by convention, z is often up. And notice that in this scheme of things, z is going up, and if we put our thumb going up, our right hand thumb going up, we point at x and then move around to y. Or if we put our thumb along the x direction and put our fingers along the y direction, and they curl around to the z direction. This is called with y into the page, this is like a right hand set for x, y, and z, or maybe sometimes we call them like I hat, j hat, and k hat as being unit vectors in each direction. Now, the way that a cross product works, I'm going to draw a picture of it first. If we have A is a vector here, and B is a vector there, then the cross product C is a vector which is perpendicular to both A and B. Now the length of C, I'm sorry, I should have said here, C is equal to the cross product of A and B, and the length of C is equal to the length of A multiplied by the length of B multiplied by sine of theta, where theta is the angle in between. Notice that in the one case where the direction of C would be hard to figure out, where A and B are parallel to each other, or in the opposite direction, then there are lots of different directions for C which would be perpendicular to A and B. Then in that case, sine of theta would be sine of 0 or sine of 180. It's 0, and so C is 0. And so whenever sine is somewhere in between 0 and 180 degrees, then there will be a unique direction which is perpendicular to A and B, and the cross product finds that direction. Okay, so how to calculate? So one way of calculating it would be with this equation here, but that is, but we can do things a bit better than that. So I want to describe 3 different ways of calculating the cross product. Okay, so the first method. Now what I'm going to do is, I think I'm going to write these down as A, B and C for one vector, and X, Y and Z for the other vector. And we're working on cross product. Now the way that I generally remember this is that you make like a determinant of the bottom two for the top line. So that's BZ minus CY for the top line. Now the next line for the middle line, it's again it's a bit like a determinant, like a 2 by 2 determinant, but this time it's CX minus AZ, and then for the bottom line it's AY minus BX. So let's just put some colours on. So for this one here, at the top, we're doing a sort of a sort of determinant with B times Z minus C times Y. For the middle one, we do a determinant this time as it's C times X minus A times Z. And finally, we have for the AY and BX, we have A times Y minus BX. For this bottom line, we have those things there coming up. So that is one way of calculating the determinant. Not the determinant, the cross product between two vectors. And if you can remember that, then that's a good way as any. Another way that people do this is to write down a 3 by 3 determinant with I, J and K along the top row, and then A, B and C and X, Y and Z. And we know that if we calculate this determinant, that determinant is going to be I hat times BZ minus YC minus J hat of AZ minus CX plus K hat of AY minus BX. And so we can get rid of the minus sign by just sort of incorporating it in there. So what we can say is that is equal to I hat of BZ minus YC plus j hat of cx minus az plus k hat of ay minus bx. So that's exactly the same formula we have, because if we would represent that as like a vector, a column vector, what we get is bz minus yc, cx minus az, and ay minus bx. So that is a way of finding it by calculating the 3 by 3 determinant. And so the method I was using there for the 3 by 3 determinant we've looked at before. So if we put a plus there and a minus there and then a plus there, so we start off by, say, for example, if we take the I hat there, we then calculate a 2 by 2 determinant of these four here. And then with the j hat, we calculate a determinant of ax, c, and z, but the minus sign comes into play, and so forth. So that's another way of remembering how to do the cross product. The one final way I wanted to show, so if this is method 2, then method 3, this only works for 3 by 3 matrices, but it's a useful way, it's like the foolproof way of getting a 3 by 3 matrix. So if we write our 3 by 3 matrix, 3 by 3 determinant again, I hat, j hat, and k hat with a, b, c, x, y, and z, then we add I hat and j hat here, and a and b and x and y. And now what we do is we do a multiplication of I hat times bz, j hat times c times x, and k hat times a times y. And so we add I hat bz, j hat cx, and k hat ay, and then we subtract. So we'll change the color for subtraction. So we take away k, b, x, and I, c, y, and j, a, z. So then we can say we're saying minus, all of them are minus I, c, y, and I'm going to put plus in here, but it's still got the minus sign on the outside. J hat is az, and again we're taking away for the k hat bx. So that's just another way of solving the determinant. This is like the foolproof way of solving a 3 by 3 determinant, which is another way to remember how to do the cross product. Okay, I mean, one question is why should we care so much about the cross product? And I want to give 2 reasons why we should care about the cross product. Let's see what color should we do. So we'll do some green. The first is that if we have some sort of shape like this, let's say we have vectors a, b, and c, and we wanted to find out the volume of some sort of parallelogram. I'm not sure what you call a parallelogram in 3 dimensions, but if you wanted to find the volume of this object, then the volume of this object is given to you by the vector c dot product with the vector a cross b. Now, depending on which order you put the vectors in, you'll get a positive or a negative answer. Of course, for a volume, it's always going to be positive. So that's one application of the dot product. Another application is in the Lorentz force on a charged particle, where the force is equal to Q times the electric field plus the velocity of the particle across the magnetic field. And I think I should just finish off with a couple of examples. If we do 1, 0, 2 cross 3, 9, minus 7, then that cross product is going to equal, so for the top line here, we're going to do 0 times minus 7 is 0, take away 2 times 9, so that's minus 18. For the next line, we're going to do 2 times 3 is 6, minus 1 times minus 7, so that's minus 7, that's plus 7, 6 plus 7, so that's plus 13, and then so she draw the lines in there for that calculation that we did. And finally, let's take the yellow color, and for this one here, we're going to do 1 times 9 minus 0 times 3, so that's 9. Now, just to check, what we can do to check that that is has worked is we can take these this vector, which is the cross product of these two here. So let's say this is C, which is A cross B. And if we take this vector C and do the dot product with A, then according to what we were thinking about before, over here, with this diagram here, it should be that C is perpendicular to A and B, and so when we do the dot product of 1, 0, 2, then indeed that equals 0. So we can also check minus 18 plus 13 and 9 and do the dot product of that with B, which is 3, 9 minus 7. It's going to be a little bit more to work out. 3 times 18 is 54, so that's minus 54. Minus 54. Now the bottom term, this is a minus 7, so we're going to calculate that one. 9 times 7 is 63, so that's minus 63. So let's write these down. Minus 54, minus 63 from the bottom term. And then this term here is going to be 90 plus 27 is 117. Oops, 117. And the total of 54 and 63 is 117. They're both negative, and we're adding plus 117, so the answer there is 0. So what we've shown there is our vector c, which is we found for the cross product of two vectors a and b, is perpendicular to both of them.